Hello, I'm Najm Sadala from the Norwegian Research Center, and I'm here to present the paper with the title "An Approach for Reducing Gas Turbines Usage by Wind Power and Energy Storage." The paper has been written in the context of oil and gas production in Norway, where most of the platforms are powered by gas turbines. These have the limitation of emitting greenhouse gases, and we want to study the potential of combining wind power and energy storage in order to reduce the emission by reducing the activity of gas turbines. I will go through these points here. I will start with the background and motivation. I will speak a little bit about the modeling, the scope of the model, the problem in general as we see it. I will go a little bit more into the details and talk about every model component, and then how we put it together into simulation cases. And finally, I will conclude the presentation. As for the motivation, this table here comes from the Norwegian statistics, where it says that per 2020, 27% of the emissions were allocated to oil and gas extractions. So the idea is to contribute into reducing this percentage. Another motivation is that the resources, the wind resources in the North Sea are important, very important. And even though they are located far from the coastline, as the plot shows, the technology exists in a way, especially the floating wind turbines can be used or could be used for powering remote platforms. Talking about the floating wind turbines, so basically, if we consider a semi-submersible structure, we think that there are possibilities of having several megawatt hour energy stored. Here, basic calculation we said that by allocating 1% of the weight of the total structure to battery storage, and by using batteries of energy density of 163 watt hour per kilo, then we are basically around the 22 megawatt hour of energy stored. So a little bit on the assumptions in a way. The model, or an overview of the model. So we see it as three major components here. First, the model, maybe the most important part, the main focus of the paper. And here we wanted to capture the dynamic of the combination of wind power, gas turbines, and batteries, given a demand, given a certain wind speed or time series on that, and as a result we get the amount of CO2 and NOx emissions, and actually the actual power or actual battery level, the actual power provided from wind turbines, and the actual power provided by the gas turbines, and the battery level, the stored energy in a way. There are also two other components. We call it a trigger and the control, which we'll explain a little bit more. But starting from the model, it's basically a microgrid with two gas turbines, one or several wind turbines, and a large battery. So the provided the demand and the wind speed, the idea is to capture the dynamic of the microgrid in terms of which part of the subsystem provides how much power, and what is the lost energy, or what is the lost power, or the lost or the deficit in power. The control is or the trigger is basically observing, in this case, the battery level. And here we put a very simple logic saying that when it reaches 60%, when the battery level is at 60%, there is no more need for gas turbines, so we can turn them off. And as the battery level goes below 30%, then there might be a need for gas turbines, so we should turn them on. The control strategy in this case is to decide which set point or which power the gas turbine should provide, and how much power should also be allocated to battery draining or charging to keep the grid in balance in a way. More in details, the gas turbine is controlled by a starting and stop signal and a target power or a reference power. At the same time, there is a configurable parameter which says about the startup time. As we know, gas turbines need some time to warm up, to be operative. And that time can vary depending on the conditions. We have not gone into the details of the conditions, but we are more interested in the delay that is caused by their start. So it's just saying that the energy or the power that you may need is not directly available, is not available at any time. So you need to account in the simulation for a warm-up period. So this is what the model captures. Otherwise, it's a simple controller that tries to reach the set point. At the same time, as an output, we get the provided power and the CO2 and NOx emissions, as shown here in the plots. You can see that the emission starts basically when the gas turbines is operational. The next component is the wind turbine. In the wind turbine is direct relation between wind speed and the CP given for actually given for a reference wind turbine. In this case, we have used the reference wind turbine of 10 megawatt from Technical University of Denmark. And we have you can see here a simple simulation showing that as the wind speed varies, the power generated also varies, and following a specific characteristic with cutting speed and cut out speed. So yeah, that's about the wind turbine. When it comes to the battery system, it's charging and discharging. Here is illustration of how it works. We go from a period of charging to a period of discharging, shown in the plot here in the blue and red, and we see how the battery charges and discharges. We have also added the notion of sort of battery resistance, and the resistance is just saying that when the battery starts getting charged, there may be some losses. So here shown in green that there are some losses because the battery is almost charged. By the way, all these components are available on GitHub, so we provide the code for that. We have not put the equations, but you can access the code. The microgrid is basically keeping things in balance. The power provided to the grid must equal the power extracted from the grid. And here we can see an example of the dynamic, where you can see from the demand to the contribution of every component. The batteries by charging or discharging, the contribution of wind turbine, and the contribution of the two gas turbines. At the same time, we also keep track on the power lost or the deficit in power. So or we should call it maybe surplus and deficit. Yes. So when it comes to the simulation cases, so we put this model together, and we use, like I mentioned earlier, two limits: 30% to start the gas turbine, 60% to turn off the gas turbines. Otherwise, we run several simulations, actually with 0 to 4 wind turbines. The case with no wind turbine is basically the base case is as it is today, and then we see the differences, how things change as we add the number of wind turbines following this control strategy. We run a simulation for 7 days, and we use a time step of 1 second. We also use a gas turbine startup of 15 minutes, so there is a delay before the gas turbine is available of 15 minutes. Like this. We move on. We can see from the base case. So this is how things could look today for a certain demand, and basically, the gas turbines are providing the necessary power for the load. As we add one wind turbine, and we can see that the battery has a certain dynamic by charging and discharging here, depending on the wind resources, of course, and the usage of gas turbines. We can also see that the emission gases are the NOx and the CO2 are correlated with the usage of gas turbines, basically. The picture changes again when we add another wind turbine. We can already see that the batteries have periods where they are fully charged. Definitely because there is sufficient wind power produced by two wind turbines, and and available wind speed, or sufficient wind speed. And again, with 3, the picture changes again, and with 4 wind turbines also. But we summarize all that in this histograms, where we can see the plot on the left is showing the power contribution for every component, for every simulation case. So, for example, when we have no wind turbines, so all the power was provided by gas turbines. With one wind turbine, we see that the picture changes a little bit, and we have a significant contribution of wind power. And the battery has also provided some, contributed into the dynamic. And then we can also see that with 4 wind turbines, so this is how basically the things vary. But with 4 wind turbines, we can see that we start having important losses. So somehow suggesting that the system is over-dimensioned in a way. 4 turbines can be too many. On the other side here, on the right side, we can see how the CO2 emissions and the NOx are reduced for a given number of wind turbines. And we can also notice that between 3 and 4 wind turbines, there is not much, there is not a significant change. There is not a significant improvement. However, 2 wind turbines, between the best case and 2 wind turbines, we can observe a significant reduction in the CO2 emissions. Well, so that's basically the simulation results, or the result that we have used for interpretation. And we can maybe conclude that okay, we have presented a simple model, though, but still it gives an idea of the possible improvements. They give an idea of how the system can be sized, what is oversized in here, and the amount of greenhouse gas emissions that can be reduced. We are aware that this work is early. We think that improvements can be in especially in the model components, make them more dynamic, more realistic, and we think that having them more towards data or more available data on the existing components will make the model much better, because we can simply either use data-driven techniques directly or have better ways to calibrate them towards towards the suggested models. When it comes to this is especially for the gas turbines. When it comes to the wind turbines, we think that there is the notion of wake that is not included here at all, and so maybe it should be because we cannot expect both wind turbines to produce the same amount for certain conditions. The winds have a direction, and they can shadow each other's. When it comes to the energy storage, they vary depending on the type of batteries. Their dynamic changes with the type of batteries, and that's why data on that can be useful. The microgrid should be on the electrical domain, though. In this paper, we have focused only on the energy and power transfer, but bringing it to the to the electrical domain, we think it can be challenging because we don't know all the aspects. We don't know all the details on the demand and actually the production, and we don't want it to be very specific to a given platform or to a given production source. So but that will be more, it will bring it into the electrical domain, will make the simulation more realistic, we'll say. The demand on data, we would pretty much like to have more details on how the demand is made. So, so actually maybe it can be decomposed into different activities, and maybe some activities can be postponed. So we can add the notion of rescheduling the needed power to optimize for CO2 reduction. As for the control, this is our maybe first priority, is to develop the control algorithm as an optimization, or define it as an optimization problem for control. Thank you for listening.